Switch mode power supply for their vac. Fascinating thing, really interesting, at least to me. So what about it? Well, if we look at the one complete one, if we have one, and it says Dyson on the case. It's glued or sealed there very well, difficult to get apart. On the back here, it sort of says, doesn't say Dyson at all, it says Salom, is that it? It says its input can be 100 to 240 at either 50 or 60 Hertz at 0.3 of an amp, and its output can be 24.35, a hundredth of a volt, at 348 milliamps, not 350, but 348. They're accurate to within a milliamp. Yeah, right. We have 16.75 volts on the other connector. So if we have a look at the connector, this thing, where have you gone? Here we are. Have a look at the connector. Then hopefully we can see our connector. If we look at the logo here, or the diagram here, we have negative is the outside of this part. Don't know if that's okay. The pin on the centre is positive. It says it's 16.75 volts. And the inside, I don't know if you can see or not, there's a metal insert there, which is the 24.35 volt. Problem with that is, if you try and measure the voltage on that pin, good chance you're going to short those together. Don't know if it'll have any effect, but certainly worries me. It don't have to be somebody, it would just be a piece of metal that gets inside, I don't know. So whether it'll damage it or not too sure. If we look inside then, what we've got, our circuit board here. First thing to do, of course, if one of these is faulty, is to check the wires on the plug. Could well be that one of those is broken, with it being taken in and out frequently. This one, which I got it apart, has been mended very neatly using a nice bit of sleeving and joining them together, so that looks okay. When I tried it though, I tested between the centre pin and the outside and found I had a short circuit. What to do? A short circuit. So I had a look, and if we look at the thing itself, we can see we've got the white wire there, black wire here, and red wire here coming away. So first thing to do with my short circuit was remove the white wire to see if in fact it was in the plug or the wire that was shorting, but no, wasn't that. What we have here are a couple of chokes with the earth 0 volts around it and the output. So if I remove that, then maybe that will remove the short circuit. Maybe the short circuit was in one of these, but no, wasn't there. Came to the other end of the board, and at the other end, I don't know if you can see this or not, what we've got are two diodes. A diode there, difficult to see underneath the wires from the transformer, and a diode here. So one diode for each circuit. So then I removed the diode. So what these are Schottky diodes. The one for the 18.6 volts I removed, the 2 amp one, and my short circuit went. So I had a look at the diode. Here's our diode. And if I test it, test my meter, buzz, test diode, buzz one way round, try it the other way round, buzz, just check that. Come on, don't disappear. Buzz. So that diode is kaput, and that was the reason probably that this power supply wasn't working. So obviously what I do is to put in another diode. Unfortunately I didn't have a 2 ampere, although if its output was only, what was it, 385 milliamps, then putting another diode in. A 2 amp diode, I don't see why that should go, but I didn't have a 2 amp, so I put two 1 amps together. Probably not necessary, but, and also could be dangerous because apparently these diodes, oops, it's lost a T. These diodes then, as they get more current, they get hotter, and as they get hotter their resistance goes down. So if you put two in parallel, then one gets hotter than the other, it takes more current, therefore it gets hotter, therefore it takes more current, and hey presto, it could disappear. But in this case where we're only using 385 milliamps, a third of the potential of one of the diodes I put in, I don't think that's going to be a problem. So put that in, put it back together, and yeah, it doesn't work. So I'd got it all back together, tested it again, still didn't work. Let's delve a little bit further into it then, see what we can find out. I did the usual of take a photo of the board, drawing where all the components are, drawing all the wires, work out what's going on, and then drew myself a circuit diagram. I decided that it was in 3 parts, so we have the high voltage stuff, the low voltage stuff, or relatively low volts if you consider 25 volts low voltage stuff, and the control circuit. If we look at the high voltage, what we have is 240 volts going in through a fuse, that's not a fuse, but never mind, through a fuse, through a varistor, thing that allows any spikes in voltage to go through it and not to affect the circuit. We then have our inevitable diode bridge, and remembering that this is rectifying the mains, so we are talking of something in the region of 400 volts. Dangerous, especially as these capacitors of course will be charged up, and once they're charged are quite likely to stay charged even if the mains is removed. So when I tested it, I used it through a transformer, mains transformer to isolating transformer, and was still very careful with these capacitors. We then move on. What we have here is the main coil. The main coil is switched on and off by this chip down at the bottom, the TNY278. The fact it's an 8 on the end means it's a 16 watt as far as I can ascertain. So that then has a MOSFET inside it which switches on and off at very high speed, thus switching the coil on and off. Of course we would expect a back EMF from this coil, so it has got this clamp circuit here. No idea how that works. Obviously there's a diode. Normally I'd just put a diode up to the top, but what the clamp circuit does, don't quite understand. Anyway, so we've got a MOSFET here switching it on and off. To control the MOSFET we have this enable input here, which comes with an opto isolator from the control circuit. At the other side we have a bypass capacitor, and we don't really need this lot, this bias coil I hope it is, which is supplying current into the TNY, so that the reason for that is you will work on its own, but if you put this on, then it reduces the power consumption on standby to something like less than 50 milliwatts. So that seems a suitable thing, and that's the reason they've probably put that on. So that's our main coil switching on and off, with our bias coil as well supplying current. We look over here then, this is the low voltage output. It comes from the coil. Most surprised about that, to see these wires coming out the top of the coil, coming across rather than doing it on the underside as I'm more used to seeing. Here's the input side of the coil, but I suppose there's no room over there for the wires that come out and come over here, so they've just taken them out the top. Sensible, I suppose. So they come out. So what we do in the coil here, so of course these from this transformer's AC, so we need a diode on each of the lines, the 25.6 and the 18.6 lines to drive it along. We've got these sort of feedback things, goodness knows what they are, they're called. Type 2A error amplifier makes that into, or at least it would if it were on a op amp, but there, not too sure. Couple of smoothing capacitors. We've got this diode here, don't understand why it's connecting the 18 volt 6 to the 25 volt 6, so if this becomes greater than that it will supply current across to it. Don't understand. Couple of Zener diodes, haven't measured those, and then another inductor up here. This inductor down here seems to be before the Zenos, this one after. Then we have another Zener diode in here. Couple more smoothing capacitors. Then some resistors here. Very low value presumably, because they're going to measure the output current in the 0 volt line. Because of course if they wanted to do it in the plus lines, then they need to have one on each, so they just do it on the 0 volts. So then we look at the control circuitry. I couldn't believe my eyes when I saw this. It's the 324 op amp, a quad op amp. Use comparators, I assume it is. So what we have is down at the bottom here are 0 volts, this is out, this is 0 volts in, and we're measuring a voltage across these three. One looks like it's an afterthought, but anyway, there's three resistors in parallel. They'll have a very small voltage drop, but that is fed into this op amp, which just looks like it's bog standard sort of thing. So that'll give us a reasonable output here into this op amp, number 3 of the 4. And when this voltage is higher, this voltage is higher than this volt, then this will become positive. If this is more positive than this, then this will become high and our LED will light. So while we're taking current, we're charging, and our charging LED lights. Why a second op amp? Not too sure, whether they just wanted to use it up or whether it was to use this circuit here where we've got a voltage regulator, a variable resistor which can drive or alter the level at which our charging LED comes on. The other two op amps then are used as a sort of OR gate to switch on the opto sensor opto sensor, opto isolator, LED, through, I think it's through those two resistors, might have got that wrong, who knows. It's from the 18.6 volt line anyway, and this one has the 25.6 and the 18.6 at the top half of a potential divider, and 0 volts down at the bottom. Why so many resistors I haven't really looked into, whether it's want to get it more accurate or whether it's a case, yeah. Anyway, whether it's more accurate I'm not too sure. So what happens is, provided these two are at the right level, then this will be high. If this is high, that means that the inverting input's higher than the non-inverting, and therefore the output will be low. And if the output is low, then this opto LED will be on. If the opto LED is on, then our chip doesn't send pulses to the transformer and stops working. So when this is on, it stops sending pulses, switching the coil, the transformer coil on and off. So provided this is high, this stops it sending signals, and therefore the coil will be off. Likewise here we have another diode so that these two can't interfere with each other, and we have potential divider. Now I can't understand this because this here is a voltage reference chip which produces 2.459 volts, which is the one that's on here. They'll just set these up to match that, but that then also is used on the top one. Anyway, that's the voltage reference chip. Why put this resistor in if you've got a voltage reference here? Why put that in? It's going to alter, one would think, unless it's just a protection, so that if this voltage goes, it pulls that high. Don't understand it. Here we have two more resistors and another resistor down at the bottom. They feed this op amp, which once again comes from our current measuring resistors. So we'll have a voltage on here. Provided the current's high, we'll get a large voltage on here, well, a relatively large voltage on here, which goes into here. And once again, if that is larger than that, then it will go 0 volts, and that will switch off our chip. So if we look at our chip at the data sheet, provided very kindly by Mouser, they've put it on the internet, so I've had a look at it. It says it's a 16 watt, contains a 700 volt MOSFET and power supply controller. It tells us that the source connects to 0 volts and it's drained to the transformer coil, as we've seen. What it has inside is an oscillator set at a frequency of about 132 kilohertz. A bit more than your 50 or 60 hertz that your normal mains is. So it's really switching at a rapid rate. The oscillator produces 2 signals, and to reduce emissions, it has frequency jitter. Now normally I'd have thought if somebody gets jitter in something, it's because they haven't done it right, but they're saying they've designed it in. Interesting. One of the pins on the chip there, and if we look at the chip, 8-pin chip, all these 4 go to the source and all connected together. This one's the drain coming in from the transistor coil, and then we have these 2 control pins. The EN pin is the one that connects to the opto isolator. So we have EN, connecting to opto-isolate a transistor. So if this is switched on, then a current flows, and if it's greater than 115 microamps, this stops switching the transformer on and off until this current goes back down again to less than 75 microamps. So it's going to pulse if this isn't on. If it isn't on, it pulses. If it is on, it doesn't pulse. Wow. So if we look at our sort of diagram we've got our V enable, our chip, our pin on our chip. If it's high, then this thing is pulsing and the drain is switching on and off. So it's switching the transformer on and off. If the occasionally misses a pulse, then that isn't going to matter, because that will reduce the output. If the output is falling, then we get more missed pulses, and if we have a very light load, then we only have very few pulses to keep the voltage correct. All in all, a fascinating project. Shame it doesn't work, but I'm not going to pursue it any further. The point being that if I have a short circuit here, then presumably the AC is going to flow through. It's going to flow through this capacitor, so presumably destroy that. It's going to go through the wrong way through the Zener, so it's going to destroy that. Wrong way through this capacitor, so it could destroy that. And worst of all, it's the supply that goes to the 324, so it could very well have destroyed that. Or it might have not destroyed anything and the whole thing might work. But I've had enough of it. Don't think it's worth pursuing it. Very sad. But that's electronics. Some you win. Well, a very few you win, and I win anyway. And quite a few like this I lose. Although I've really enjoyed going through it, sorting it out, and trying to work out what's going on. Oh well, bye for now. Bye.